Alrighty, welcome to ECE353 Systems Software. So, first lecture, well I guess this is the first and the second lecture since we're here for 2 hours. So let's start it off easy. So, I am John, your instructor. That is my last name. It is a bit of a disaster. So, if you don't know how to pronounce it, just looking at it, do not feel bad. I didn't even know how to pronounce it myself until I was done with undergrad. And I had a nice trip to Iceland where I gave the nice Icelandic man my passport, and he asked me to pronounce my last name for him. I did, and he said it was wrong. So, I pronounce it the good way to, or the perfectly acceptable way to pronounce it for me is Elfson. So elf, it's just Christmas. Elf should be still kind of in your head. Speakers are weird, okay. So elf still in your head, and then sin, Elfson, boom, easy. Everyone can pronounce that right, especially just off of Christmas. And then if you're in the unfortunate scenario where you have to spell it, the easy way to spell it is to take the L and the F, shove it over, and then shove a yo in there, and boom, that's how you spell my last name. So hopefully you don't have to spell it, but if you have the unfortunate, if you're in the unfortunate situation where you have to spell it, that is a good way to remember how to spell it. All right, why are we doing system software, more specifically for this course, operating systems? So, understanding operating systems will make you a better programmer no matter what type of software you write in, no matter what language you write it in. Because, this is universally true, there are only 2 types of software in the world. You either are writing software that interacts with the operating system, or if you're not writing software that's interacting with the operating system, guess what? You're writing an operating system. So this course is relevant no matter what type of software you write. So some important URLs for course resources. I've seen like over a quarter of you have already found the links and have gone into the Discord and signed up for everything, so that's great. But very important, go to compbench.gg. That will tie all of our resources together. The lectures are all available on my website, which is elfson.com. Again, you can use the link. Everything's also on Quarkus, so these links are also on Quarkus, so you don't have to actually spell my last name. But you can just go to elfson.com, it'll be a button there, or go to courses, ECE353. For the labs, all of the content for the labs are on that site there. Again, it is provided for you from Quarkus, so all the other links and information that should be private, which is basically just my email address, are all on Quarkus. Other than that, grades will probably sync to Quarkus, and other than that, I don't really use Quarkus. I do use labs on GitHub, so you'll need a GitHub account. Discussion, I don't like Piazza. I use Discord, so Discord is there. Again, like a quarter of you are already in there. There is a bot. If you like anonymous message, there's a bot on there. You can type /anon and then a message, and the bot will anonymize you. So then I don't have to do Piazza. And then if you like Piazza forums, there's Discord forums. You can use those. And then lastly, there is YouTube. So things are recorded. They're live streamed. If you're sick, you don't have to come in, but please still come in. So for the anonymous Discord message, again, I know some of you, it's like weird. As soon as I started doing Discord, I assumed all of you were anonymous to each other, but it turns out you're friends outside of class, which is weird, and have other Discord servers. So again, if you want to be anonymized, we fix that. It's just /anon, your message, the bot anonymizes you, and it will do that in the current channel you are in. Lecture attendance, still important. Much faster for me to get feedback from you and clarify if anything is unclear. Even if you just sit there, I can see if your face is confused. I get very, very quick feedback just looking at your faces. Or if you want to ask a question, really easy if you are in class. I also have Discord, the Discord lectures channel open beside me. I can also take questions from Discord, although If no one starts using it, I will stop reading it, and I will probably miss any questions that are on Discord. Throughout the course, the reason I am here and all the fun stuff is there's built-in time for live coding. We'll be able to explain, like Bob Ross, any happy accidents we make, try and break my system. You get bonus points if you break my computer. So that is an incentive for you. So if there's anything else I can do to make attending a better experience, please let me know. First thing, that thing's annoying. Is that loud enough? That's still loud enough? Okay, that's probably better than that thing, right? Okay, good. Screw that thing. This room's weird. All right, so for evaluation for the course, there are 6 labs. Lab 0 is basically just intro to the environment, worth 1%. You just have to answer 5 very, very, very short questions on CrowdMark. You should have got an invite for that as well. After you do lab 0, which is just setting up your development environment. And then we have 6 labs, all worth 4%. And then I originally had a midterm. I guess you guys aren't, EngSci is not a department, where you, the division of EngSci was like, yeah, their midterm week is absolute hell. So I'm like, well, I can move it. And then I just got rid of the midterm. Instead, we'll do 2 tests. We'll do them in lecture time, and we will split it out. We'll do one in week, I think that's week 4 and week 8. So instead of a midterm, we have a tri-term, I guess. So we're going to have 2 tests worth 12.5% each instead of just one midterm worth 25% each. So your midterm week is not absolute hell, and you might actually enjoy reading week, at least for this course. Then final exam worth 50% because it has to be worth a lot of grades, yada, yada, yada. And then again, the tests, the split midterm is done in lecture time. Unfortunately, it's the Wednesday 1-hour slot, so it will only be like 45 minutes, but it will be already February 12th and March 12th. So also, academic honesty, again, this is like standard boilerplate. You should be used to it by now. So you can study together, discuss concepts on Discord. Please don't post your code on Discord. Please don't airdrop your code to your friend and then claim you did not airdrop your code to your friend. That leads to a very lengthy discussion with me that I do not want to have with you. I am happy to talk to you in my office. I just don't want to be forced to talk to you in my office because of some academic integrity thing. You always just ask for help instead, or if you're trying to submit things the last minute, just take the L. They're only worth 4% or something like that. Just take it. You do not want to do the academic integrity thing. It is a pain for me and you and everyone involved. And it will only hurt you because the majority of the marks are from the exams, where you have to explain why and not just spit out some code. So if you need, this course is done mostly in, well, pretty much always in C. So these are recommended books if you need some catching up to do. You shouldn't need any external materials. This is only if you need it to really catch up. There's Operating Systems 3 Easy Pieces, which can help complement the lectures if you want another point of view or you just happen to like books instead. More or less the topics pretty much match up. The topics are pretty much the same as the topics we have. You should be able to find exactly where the relevant material is. And if you don't know C, well, there's the C programming language book in case you need to have a refresher on C. Everyone's used C before, right? Ish? Okay, so we should be all right. C is a fairly simple language. And if you need more practice on it, you'll get it in this course. So again, skills, you should practice again if needed. C programming and debugging, mostly thinking through your program, knowing that computers do not execute magically and that things happen in a very logical fashion. Your CPU does not have a bug in it. Your compiler doesn't have a bug in it. Very likely you won't encounter that. So anything you should be able to reason through. There is a reason why things are happening. And the great thing about this course is this is the first course where you can actually explain what the hell is going on when things go awry. Being able to convert between binary, hex, and decimal, probably should know how to do that. Probably doesn't actually matter, but actually knowing hex will probably help you a bit understanding things, since that's how computers express information. Some parts will be slightly low level to explain it, so being able to do those conversions will be very, very helpful. You did kind of a lower level course. You should know, if you see big endian, little endian, won't actually come up with this course, but as some background knowledge, you should know what those things are. This is an important one because I don't know why students, especially in the operating system course, do not know this one, but memory is byte addressable. A pointer is just basically an address. Memory is basically an array of bytes, and a address is just like an index into that array of bytes. So you can only address memory 1 byte at a time. So an address or pointer, it's just an index into an array, and memory just stores bytes. So index 0 or memory address 0 is 1 byte, 1 is the next byte, so on and so forth. Just computers have a lot of memory, so the number of addresses is very, very large. And again, please provide feedback. This course can be quite challenging since we are going into the nitty-gritty details, well, not really nitty-gritty details, of how software actually works. And please let me know if anything is unclear. The great thing about this course is you can pretty much ask any question about any software you like, because, like I said at the beginning, you either write programs that interact with an operating system or you are writing the operating system. So you should be able to explain what any other program is doing, no matter what language it is written in. So you can ask lots of fun questions. Again, all programs interact with the operating system. We will see a bit of that today. And by the end of this course, you will be a better programmer. So diving into a bit of the content. So what the hell is an operating system? Well, at the core of it, an operating system just manages resources. So you have your operating system sitting in the middle of your application and hardware. These are ECE specific numbers. You can convert them for ENGSci, but in first year, you've written applications. If you've used Python or anything like that, you've written applications that interact with the operating system and request some type of resources, memory, CPU, maybe disk, maybe network, something like that. And they interact with the operating system, and you treat the operating system as some magical black box that just did the right thing. Then in second year, you had more of the hardware courses where you had assembly and things like that. And that was how to actually interact directly with the hardware, with memory mapped I/O and all those fun things, and registers, and everyone remembers all that fun stuff, right? Interrupts, all that joyous, joyous stuff. So we won't really-ish get into interrupts and all that. We will be tying both pieces together. So the operating system sits in the middle here. Some of it interacts with the hardware. Again, we won't go into too much detail. And then applications interact with your operating system, and the operating system returns some result back to them. So in this course, there are 3 main concepts. The first one, which will come up again and again and again and again, is virtualization. And that is where I share one resource, CPU, memory, something like that, by mimicking many independent copies. And then everyone thinks they are accessing something like all of RAM, or they think they have exclusive access to the CPU, even though they don't. They just have a fake copy of that they think they can just use independently without worrying about any other programs running or anything like that. In a few weeks, we'll get into concurrency. That's handling multiple things happening at the same time. That is where real programming starts to take place, and where our brains will start to break a little bit, and where we will be enlightened by the world of real programming. Then, after we're enlightened, we get to end the course with persistence, retaining data consistency even without power. That will be a nice kind of palate cleanser by the end of all the hard topics. So I was introduced to this quote in my 4th year, and it rings really, 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 really true. So I'll introduce this to you in 3rd year. So all problems in computer science can be solved by another level of indirection. What does that mean? Well, if I have a really hard problem, I just make up some name for how to solve that problem. I describe what it should do, and then I solve that problem instead and try and map all the difficult things onto that problem. So the first abstraction we have is if we are the operating system, we need to figure out how to actually run a program. So the first abstraction is called a process. So we've all had a program before, our C program, our Python program that we want to run. That's our file containing all the instructions and data required to actually run this program. And then if we actually run it, we give a name for the task of actually running it, and that is a process. It is just an instance of running a program, and the operating system takes care of managing processes. So this will be the main abstraction we visit over and over and over again and try and demystify exactly what is in a process. So the basic requirements for a process, everyone, I hope, knows what a stack is and what a heap is. Yes? Good, some thumbs up. So the stack and the heap, memory associated with that, they're all managed within a process. And then a process, this is going to be the first virtualization we use. It's basically each process has its own set of virtual CPUs because, well, that CPU core with its set of registers may be running multiple processes concurrently. So you don't have to worry about in your program if your registers change out from under you, in which case, if your registers randomly change, your program probably would never work. So your process actually uses something called virtual registers. So it thinks it's the only one changing the registers. That's how it can actually argue that the program is actually running correctly. So my first question for you is how are you able to run 2 different programs at the same time where the programs themselves are the exact same? So for example, hello world and another one that counts up every second. Oh, in this case, they're 2 different programs. So if I have 2 different programs running at the same time, and you were the operating system, given you know nothing, how might you try to run these 2 things at the exact same time or using only one CPU? So each of these programs that needs their own stack and heap, right? Well, I only have a certain amount of memory. So maybe if I'm the operating system, I say where the stack is and the heap is for the hello world program. Maybe I say where the stack and the heap is for the count program, and then just let them just run their code, maintain some virtual registers or anything like that so that they actually run successfully, and then I just let them run, right? That seems reasonable to everyone. Reasonable how our computer could work. But some questions we might have as well, is that actually true? Does the operating system allocate different stacks for each process? So the stacks, they use memory. Is it physical memory? One option is that, like I said, the operating system just allocates, just chooses, hey, you use this physical memory, use this physical memory, and here's some unused memory you guys can use from the stack. Is there some issues with that if I just say, hey, program 1, use this physical memory, program 2, use this physical memory? Has anyone used C before and had a segmentation fault or anything like that, where you just randomly use memory addresses? So if I do something like this, is there anything preventing one program from reading another program's memory? Probably not, right? Which is probably bad for a number of reasons, mostly security, isolation, all that. What about if one of these programs was Chrome and you just download a random program from the internet, and then it can actually read the memory Chrome's using, read your bank account, and all of that fun stuff? Probably no good for security. So what about some global variables? So before I go, actually it's already ruined here. So global variables, you might think they are some magical thing that, you define a global variable. Whenever you run your program, the operating system decides what address to use for it, and some magical stuff happens. None of that actually happens. What actually happens for global variables is the compiler just picks a random memory address for each global variable when you compile it. When you compile it, it's the same program. So you run it, it's the same memory address every single time. Well, if I was using physical memory, I could still deal with global variables. Like my compiler would probably need like a global registry of addresses to use. There'd be some issues with that if the compiler had to know of every single global variable across every single program on my computer. That's probably really bad. So what that would maybe look like is, hey, let's say process 1, when it runs, uses this region of memory. Process 2 gets this region of physical memory that it can use. And then those two processes only get that much memory. If they want more, too bad. And they also have to share with other programs. And then you might have other programs you want to run on your computer and be like, oh no, well, I want to run Chrome and Firefox. Chrome needs a lot of memory, so maybe I just allocate a whole bunch of memory for Chrome to use for its global variables and everything like that. And then maybe I have some space for Firefox for its global variables and everything like that. This also wouldn't work for several reasons. One being, well, this memory would have to be reserved for Chrome, no matter if it's running or not, right? Because you don't want any collisions. You don't want some other program modifying Chrome's memory. So you have to make sure it's in a different physical address, or it's using different physical addresses, no matter if it's running or not. Second problem is you couldn't actually run two instances of Chrome because they would both be trying to use the same memory addresses and nothing would actually work. So let's actually demonstrate what happens if we are running two instances of the same program. So let's switch over here. So first off, let's see how well we know C. Whoops, that is not the right one. Come on. What? Display. There we go. All right, so let's see how well we know C. So we got include standard IO, include, I'll show you why I'm using this for, and then now we have static int global equals 0. So let's see how well they taught you C. Anyone tell me what static means here? No Googling. Yeah, sure.
Oh, okay.
I saw you Google.
No.
Oh. Okay.
As soon as you said that, I was hands off. Well, I mean, when it's in a function, it means there's only ever one instance of the variable for every function call.
Yeah.
In a global scope, I'm not honestly too sure, but that's the extent of my knowledge.
Yeah.
It's almost like a constant, I feel, like static. It's all static.
Static is almost like a constant. Nope. Yeah. Accessed by all instances of a class. So we're using C. There's no such thing as a class. Yeah.
Does it have something to do with like other files being able to see the variable?
Other files being able to see the file. Close enough. So if I didn't have static there, it'd be int global, right? It'd be a global variable. If I put static in front of a global variable in C, that means, in fancy terms, it means no external linkage. In plain English, it means no other .c file can use that global variable. So only this file can use that global variable. It's basically C's scuffed way of doing like C++ private things-ish. But C++ doesn't, or C doesn't have classes or anything like that. So that is what static does there. Just in the habit of using, if I just use that global variable in only this C file, good idea to use static here. Another reason why is if I stop using it, the compiler will give me a warning that I'm not using a static variable because it knows it can only be used in this file, so it will tell you if it's actually unused. Anyways, that was a brief detour. So the rest of it we should be able to read. Okay, so we got int main here, so takes no arguments and then returns an int. We'll be learning what that is too. Then first line, int local equals 0. Anyone want to tell me what that does? Uh-oh. Yeah. Yeah, initializes a new variable called local and initializes 0 to it. Where in memory is local? Yeah. The stack, right? It's on the stack. So local variables are always on the stack. So you might have thought that was like a detail or like a quiz thing for you in C before. Trust me, in this course, it will become very, very relevant. Not super relevant right now, but it will be. All right, now I have well 1. By default, C doesn't have true or false. I have to import true or false. If you don't want to import true or false, you can just use 1 for true, 0 for false. So while 1, infinite loop, I do ++ local, ++ global. Well, I wonder who taught you C. Anyone know what the difference between ++ local and local ++ is? Yeah.
The value is, if you do ++ local, the value changes before you access the value. If you do local ++, the value access changes after the number is +1.
The value access.
Or the value before.
So if local is 0, and I do local ++, this is an ++ local is an expression, right? Everyone knows what I mean by expression in C. So what is the result of that expression, ++ local, if local is equal to 0? Uh-oh. Yeah. 1, incorrect. Or wait, no, correct, sorry. Incorrect, sorry. It is 1. So what is the value of local ++? 0. I confused it. See, I confused myself. So that is the only difference between local and local ++. It's the value of the expression, whether it comes before or after. Both of them actually do increment local by 1. It's just whatever the value of the expression is. So basically, for a number of reasons, you should always use the prefix version instead of the postfix version, because the postfix can actually introduce weird performance issues. We won't be going over to this and that in this course, but don't worry about it for now. Just know that you should probably prefer this form. Then here, I just print off the value of the local and the global variable, and then sleep for a second. So that will just pause for a second, and then go again. This is an infinite loop. It should increase it from 1 to 2 and keep on going. So if I run this, look, I mean, it works how you think it should, right? Local 6, 7, 8, So here is our first thought experiment. I can open a new terminal here and verify that this is still running. So it's all the way up to 25 now. Now, what should happen if I run the program again? Should it still, will this print start at 30 or whatever it is up to now, or restart at 0? Restart at 0 is what you would expect, right? Even if they're running at the same time. So it restarts at 0. Then we got global equal 1, 5, 7, 8, 9, so on. While the other one is still running. So the other one's up to like 50 by now. But it's the same program, still running. Well, let's try and get into how this is running. So I said for global variables, the compiler just kind of picks a random memory address. If it's physical memory addresses, well, this global variable, right, it's now 85 over here and 41 here. They are clearly independent, so they must be different physical memory addresses, right? That's the only way this would work. Otherwise, it'd be the same value. So, well, if I was inquisitive, what I might do is, well, I can see lets me take the address of stuff. Let's just print the address of the pointers. So let's say I modify the program, and actually let's just do a little copy pasta. So instead of just the value of the local, I will print the address of the local, whoops, and then the address of the global. So I'll change the format specifier from D to P to indicate pointer. Then I have to typecast it to void star to make the C gods happy, because void star is basically pointer. I don't care, because really if we take the pointer to local, it's a pointer to an int. But you know, C is dumb, so we have to tell it that it's a void star. So now I'm going to print the address of local and global. So from seeing both of them run, has to be a different memory address, right? So actually, let's start off less interesting. So let's only print local first. So we'll print local first. And then here I will do this and then comment it out. All right, so let's compile. All right, so, oops. So now let's run it again. So I get this ugly address where it's something something 6C. If I go to the other terminal and run it here, it's something 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 0C. So different memory addresses, could be different physical memory addresses. I don't really know at this point. But this makes sense, right? Have to be different addresses because, well, they're not interfering with each other, right? So that makes sense to everyone? All right, then let's try and find our first mystery. So let's print the address of the global variable. So we will recompile. Oops, what did I do? Oh, I spelt build wrong, okay. All right, so now I'm printing off the address of the global. In this one, it is 440030. It's all the way up at, let's see, 10 now. Now I will run it in this terminal. It is 440030. Is that the same address? Yeah. Any guesses as to what is happening here? How can two running programs use the exact same memory address, but clearly the values are different, right? They're independent in each process. Yeah. Yeah, they must be using virtualization. So they must have access to virtual memory. So each of your programs, when they run, they think they have access to all of memory. But really, the operating system is the one managing physical memory and actually mapping virtual addresses to physical addresses. So even though the virtual address in both the processes is the exact same address, your operating system maps it to different physical addresses for each different process. Don't worry about how that actually works yet. We just uncovered that virtual memory does exist. It will probably take us about 5 weeks to, no, not 5 weeks. Probably take us about 3 weeks to actually start talking about virtual memory. But all we need to know right now is that it clearly exists because two programs were using the exact same memory address, but they weren't interfering with each other. Also gives us some nice benefits where no program can read any other program's memory because, well, each process has its own view of memory, and you can't actually read someone else's memory if you're using virtual addresses. Again, don't worry about any of the details for now. We will explore them later in the course. So we found that the address of the local was different between the two processes. The address of the global was the same between the processes. So we have something like virtual memory. So if a process is basically the operating system keeping track of everything needed to run a program, what are other things that the operating system may have to keep track of in a process? So think of other resources your program may use. All right, our break is done. That was a quick 10 minutes. All righty. There, let's blow your ears out. All right, let us continue. So, let's actually run this program and verify that this does actually do hello world. So, if I look at this random collection of bytes is only 168, I believe. So, it's saved as a file on my machine as hello world ARch64 because I have a Mac laptop, so it's ARM. So if I go here and try to run it, looks like hello world, right? That's the hello world everyone knows and probably not loves, but knows of. So I run it, seems to run very well, just prints hello world every single time. Really, really, really small. So this part is mostly just for fun. I have to dive into the file format a bit. I will never ask you about file formats, so you can sit back and relax for the last bit of this lecture. I will tell you the few important parts you actually need to know. So I will try and explain every single byte of this, and I'll gloss over some of it, but we already know the magical first 4 bytes that are, whatever, 127 and then ELF. So, one aside, there's 3 major ISAs or instruction set architectures in use today. It's basically machine code or numbers the CPU understands. There's x86, aka AMD 64, because they came out with the 64-bit x86 CPU first. That's for desktops, non-Apple laptops, for the most part, unless you have a Snapdragon. And then servers, everything like that. Then there's ARch64, aka ARM64, which is basically what your phones are using, your tablets, or Apple laptops are using. And then there's RISC-V, which is an open source implementation, kind of similar to ARM, but you could actually make your own CPU with it without paying ARM millions of dollars. So we'll touch on all of them in this course, not in any detail, so don't worry. You don't have to write any assembly in this course, but we will read a very, very small, tiny bit of it. So the next abstraction we kind of saw in that read for file things is called a file descriptor, that FD. So since our processes are independent, we need a way to transfer bytes to and from our processes to other processes. Otherwise, if your process just ran completely independently, it would do some calculation that you would never ever see, and it would just be, heating up your laptop for no good reason. So even hello world needs to communicate with a different process. So to communicate with a different process, this is the important part, the one term to know. Again, we'll revisit it later. Is IPC, stands for inter-process communication. It's how to transfer data between 2 processes. So your hello world program is actually transferring the string hello world to your terminal, which is then responsible for printing it to your monitor. And the reason we use a terminal is because we don't have to be concerned with how our video card works or anything like that. We just give it text and the terminal figures it out for us. Then the file descriptor. The file descriptor is basically an abstraction for any type of resource we can read bytes to, read bytes from or write bytes to. So the same abstraction is used for a file, interacting with your terminal, using internet connections, using your network card, everything like that will be using a file descriptor for actually communicating between different processes. So in this case for now, let's just consider a file descriptor representing a file or your terminal. So operating systems are a bit weird. I just can't call a random C function and hope it works because, well, the core part of the operating system is actually managing hardware, which your program is not allowed to do. So to make requests to the operating system, the only way to do this is to do something that kind of looks like a function call, but is a bit special, and it's called a system call. So it's a bit special. We'll get into the detail of how this works, but we can represent system calls as if they were regular C functions and use them as such, but the way they work is a little bit different. So here are two system calls you need for hello world, and this is universal no matter what. So the first system call you need is something called write. It takes 3 arguments. A first one is a file descriptor, so that's just something that represents a file or your terminal. And then it takes a array of bytes. In this case, C, it doesn't care, it just wants a pointer. So the way C indicates the type of a pointer it doesn't care about is just void star. Again, that's just C. It's a pointer, I don't care what it points to. And then const means we will not modify any of the values that this points to. So this is saying it's not going to modify it, don't worry. And then the third argument is count, or how many bytes to read from this array of bytes. So it should write all of those bytes to whatever this file descriptor represents. In this case, let's just assume it's our terminal. And then the next system call we need to make is something called exit group that takes a single argument, int status, and that is the only way to stop executing a process. So that exits the current process and sets the exit status code. If you've written C, int main, that's the int of int main. So the number eventually goes to this system call, and it should be an exit status code between, on Linux, 0 to 255, where 0 indicates no issues, and non-zero indicates there was some type of error with your program, just by convention. So, oh, yep.
Yeah, so did we define what a system call is, or are we just saying any C function is a system call?
So for now, system calls, they just look like C functions. We'll define what they are in a bit and see how they work in a bit. But from our point of view right now, they behave exactly the same as C function calls. I can just call them, I get a value back. Nothing's different. But they are a little bit special. All right, so if I was to write a hypothetical hello world program without C, by convention, whenever you run a process, there are a few file descriptors that are just defined by convention. And these you will become familiar with throughout this course. This is more magic numbers that you will remember. So there's a magical file descriptor 0 that represents standard input. So that's something I can read to. And then standard output is just the number 1. It's file descriptor 1. I can write bytes to there. And then standard error is just the number 2. So your printf, that goes to standard out, or in Java, or in Python, or whatever. When it gets to the operating system, it just goes to file descriptor 1, at least on Linux. So if I was to write a magical C function that just started executing and called it _start, and it doesn't take any arguments or return any arguments, if I was to write hello world without a main and assume execution starts in the start function, the minimal hello world program I could write is just write to file descriptor 1, which is standard output, and then write the string hello world with a new line. So this would be, a standard C string. So it's basically just an array of chars and then a pointer to that. So you can just use it as an array of chars. And then I have to say how many characters to print, or how many bytes to print from this array of chars. So 12 would be HELLO space WORLD, and then \n, that's just one character, that's a new line. So in total, that's 12. And then that's all I do, and then I exit group. So that's all my process does, is just print hello world and exits group with 0, indicating that there's no error. So if I was to write the most basic hello world program that interacted directly with my operating system, this would be it, not the C hello world, which probably looks more like, let's drag this down. So the normal C hello world just looks like that, right? Int main printf, return 0. But if I was interacting directly with the operating system, it would look like write 1, hello world, new line, number of bytes, exit group 4. You can see kind of the niceties of C. You don't have to tell C, how many bytes to write or anything like that. It figures it out for you. All right. So this goes to another aside that you don't really need to know, but it will be important for figuring out system calls. So you've probably heard of an API before. Probably haven't heard of an ABI before, or maybe you have. But an API, application programming interface, basically just abstracts the details and ignores them and just describes the arguments and the return value of a function. So for instance, a function takes 2 integer arguments and returns an integer. That would be an example of an API. One's named X, the other name's Y. That's an API. An ABI, or application binary interface, specifies the exact details, specifically how to pass arguments and where the return value is. So if you've written assembly, you probably remember, which registers are callee saved, which are caller saved, which ones do I have to save, which argument goes where, the C calling convention where arguments are passed on the stack in right to left order. All the details are in the ABI, and both the caller and the callee have to agree, otherwise things will not work. Usually you don't have to pay attention to the ABI, but sometimes you actually need to pay attention to it because the details do matter. So there is a different system call ABI, specifically for Linux on ARM64. You have to go ahead and look this up. These operating systems, because they're part of the operating systems, they're not normal C functions. They don't have an address to call. So when you compile, a call to printf, that's just call to a random memory address. Well, you can't actually, the operating system doesn't load itself into your own virtual memory address. There's no address to call. So these functions, what we do to call them is we generate an interrupt to the OS, and then the OS thankfully handles the interrupt for us, and then actually performs whatever we request, and then returns back to us kind of as if we called a function. So your program can generate an interrupt by using the special instruction, specifically on ARM, called SVC. So that's a call to the supervisor or call to the operating system. And the ABI is that it passes arguments in registers. So register X8, that contains the number of the system call to use. So every single function, each different name gets assigned a different number. So the write function could be, number 64. Exit group can be number 200 and something like that. The number goes in that register, and that is how the operating system knows what function to actually perform. And then it actually allows you to have 6 arguments in register X0 all the way up to X5. And those are all the arguments you can pass to the operating system function. So what are some obvious limitations of this? Compared to C specifically. Yeah.
You might want more arguments.
Yeah, what about if I want a 7th argument? Well, in this case, too bad. All the registers, too, are all the same size on ARM64. There's 64-bit registers, or 8 bytes. Well, what about if I wanted to use a value that's bigger than 8 bytes, like 16 bytes? Well, it doesn't fit in a register. I either have to combine registers in a weird way. That won't work here if they're all different arguments. So I can't use anything bigger than a register. And anything smaller than a register, like if I want to use a 1-byte argument, well, I'm basically wasting the other 7 bytes of a register if I only use 1 byte. So it's not terribly flexible, but it doesn't have to be that flexible. But it does have some limitations here. This is also why we don't use it, and we use like C most of the time, so we don't have these weird limitations. All right, so this is the last aside. I don't know really why this is here, but just for interest's sake, the C ABI or calling convention for x86, system calls only use registers. C is mostly stack-based. Arguments are pushed on the stack in left to right order. There's some registers that are caller saved, remaining registers that are callee saved. Although that's not exactly true, some arguments may be passed in registers instead of the stack for performance reasons, because using memory is much slower than the stack. You can see Wikipedia for details. There's lots of conventions. They just have to agree. Some advantages this gives us over the system call ABI. We can have any number of arguments, and if we use a stack, they can all be different sizes. It's all hunky-dory and all fine. Disadvantages is that, well, if we use a stack, it's going to be a bit slower. So, going into the file format. So programs on Linux, or PlayStation, I guess, use ELF file format. It stands for something exceedingly boring. ELF stands for Executable and Linkable Format. They're not very creative. It specifies both executables and libraries, so that's why, any of my programs and the standard C library both start with the same thing. Always starts with 7F, and then these hex characters, which are ELF. In fact, if you look at the ASCII tables, 7F is actually defined. It's just not a printable character. It actually represents the delete character. And that's just a way to signify that, hey, you shouldn't interpret this as like a plain text file, because the first character is something you can't print. And again, these first 4 bytes are just called magic. That's the only way your computer actually knows what this file is. There's lots of different file formats that have many different number of bytes. You can actually look at Wikipedia, the list of file signatures, if you don't want to call it magic. Magic's a bit more of a fun term. PDF files actually all start with the same 5 bytes. So there's actually, if I read the next 5th byte, it would always be a dash. And that's just what every single PDF file on the planet starts with. Images have their own format. They all start with magic, JPEGs, I don't know. I forget their starting character, but some starting character, then JPG. Everything has that. Sorry to dispel the magic from you, but you can go ahead and explore that if you're weird like me. All right, so what I argued before is that our bytes represent that ELF file for that Hello World program. What this actually does is tell the operating system to load that entire executable into memory at some address I just picked willy-nilly. I just picked 10,000 in hex because I felt like it. And then there's part of that ELF file format that describes the header. So that describes information about that ELF file. It's 64 bytes by definition if you look at the specification for it. And then a program header, which you need for executables, is 56 bytes. So just information about this executable takes up 120 bytes in total. And that's only to describe what's in the file, not actually doing anything important like representing data or instructions. If you dive into it, the next 36 bytes are instructions. And then there's actually 12 bytes for the string hello world with that new line. So if I load the entire thing into memory starting at address 10,000 hex, the first 120 bytes are loaded into memory as well. But that just describes the contents of the files. Instructions would start at byte 120 because that's the first byte after all of the information about the file. And 36 bytes later, it means the string data starts at hex 10,000 9C because 9C is 156. So that's the last 12 bytes of that file. If you want to visit all of the gory details, there's this program called readelf, and you can do readelf-A and read all of the gory details about it. So this will tell you what's in the header file. So it says like, hey, what's the data in this? This is where Little Indian comes into play. What's the version? What operating system does this run in? What is it? Oh, it's an executable file. What's the ISA? What version is it? Where do I start executing? Which is that address where the start of the instructions are. A whole bunch of boring information that if you're a masochist, you can look at the details We will ignore them for now. Just know you can access them if you want. So visually, how those random bytes look is the first 64 bytes, again, visually. These all represent information about the executable. So all of the blue space that's wasted there. And then these cyan bytes, the other 56, just say, hey, please load into memory at this address. I just said loaded into memory at starting at 10,000 hex. That's basically all that does. And then the next few bytes that are actually doing things that take up the least amount of, well, the second least amount of space are the actual instructions to actually do the write and the exit. We'll get into how we do that. And then finally at the end is the actual data for the string itself. So if I disassemble those 36 bytes on an inline disassembler or some local disassembler, thankfully, you don't have to do this in your course, but if you get into like reverse engineering and like exploits and all sorts of stuff, you probably will do stuff like that. But basically, if I disassembled these instructions, this is what I would get. And what they do is, well, this uses the system call ABI. So what we can see here is what move just does is it does an immediate move of this value into this register. So it's setting register x8 equal to hex 40, which is decimal 64, which, if we remember before, is just the magical system call number. So I wanted to do, if I'm doing hello world, I'm doing write first. So write is just system call number 64. Then x0 is the first argument. Standard out is just 1. The second argument is the address of the string. So on ARM, I can't do a move of a like very large value because all my instructions are only 32-bit. So I have to break up setting x1 into 2 different instructions. Basically, all this will do is just set x1 equal to the address of that, the address of the string, which is 10,009C. And then the last argument is how many bytes to read from that address. And it's just C, which is 12. And then I do this SVC instruction. So this does the system call. After this, I should see hello world on my terminal. And after the operating system's done writing it to my terminal, it just returns here and keeps on executing kind of as if that was a function call. Then I want to do exit group. So that's a different system call number. So I load x8 with the magic number 94. So that's the number for exit group. First argument should be 0. And then I do SVC. And there's a number here, but basically that number's never used. So we just set it to 0. And then this does exit group and then exits my program. And that's as complicated as it gets for hello world. So the final 12 bytes are the hello world string itself, ASCII encoded. It's this, followed by a new line. That's what A is. And a weird low-level ASCII tip is bit 5 indicates whether or not it's a upper or lowercase letter. The values differ by 32. If you're a giant nerd like me, and this is how they designed it because computers weren't that powerful back in the day, so they designed ASCII in a way that it was easy to check if a letter is capital or not by just checking a single bit, which is pretty much the fastest thing you can do. So uppercase letters, bit 5 is 0. Lowercase letters, bit 5 is 1. So I don't know why I told you that. Again, I'm weird. So that accounts for every single byte of the program, and we can see what C does. So already we can spot a difference between strings in our example compared to C. Because as they've taught you, strings in C are null terminated, right? Is this string null terminated? Whoops. Yeah, this string's not null terminated, right? I had to tell the operating system how many bytes to actually read from the string instead of being implicitly terminated by a null byte. So the C program designers really, really regret that C string format because it's actually quite terrible and causes a whole lot of problems. It's a lot easier to keep track of the size of it independently. If you program it right, which I guess is a stretch. But let's see what happens. So that's every byte. So let's verify that I'm not lying to you. Again, I will run this program, prints hello world. And then if I look at it, the size of the file is right here. So it is only 168 bytes. So you've been told C, super efficient, right? Yeah.
Why are the file header and program headers so large?
By specification.
Oh, okay.
To represent all the flexibility you need for file formats. Okay, so yeah, so this is 168 bytes. This program, that looks like hello world to everyone, right? So let's compile it. So compiled it, we can actually do like the read 4 bytes, verify that it is indeed, that C has produced a hello world file. It's an ELF file. All right, cool. Looks like an ELF file. Prints hello world. C is an efficient language. Anyone want to guess how big this program is? It just prints hello world, so it should do the same thing as mine does, right? So anyone thinks the C version is 200 bytes or less, so it's around the same as mine. No one thinks C is as efficient as me? Okay. How many people think the executable C produced is less than 1,000 bytes? 1, 2, 3, 4, 5, 6, 7, 8. All right. Who thinks it's less than 10,000 bytes? We're getting closer to a quarter. All right. What about 50,000 or less bytes for hello world? Should be more hands than before. All right, less than 100,000 bytes. We're losing confidence in C. All right. So let's just see how big this is. So ls-ls. 199K, that is 1,000. So it's almost a megabyte for hello world. Hello world. Like 0.1 megabytes. My hello world. 168 bytes. Any difference? What the hell is going on? Who said C was an efficient language? Someone lied to you at some point, right? All right, so the fun part about this is we actually get to dispel what the hell is going on here. So I've just been saying the operating system, the operating system. It's time to talk about actual specific names. So an operating system is actually a whole bunch of different things. One thing that is in part of the operating system is something called the kernel, and it is the core part of your operating system. So on your CPU, there is a special privilege mode called kernel mode, and that specifies what instructions your CPU is allowed to execute. So kernel mode allows you to access instructions that actually interact directly with the hardware. So if you try, even if you knew what the instruction was and you tried to use it in your executable, you would get an error of illegal instruction because your program is not allowed to actually modify hardware. So some part of your operating system runs in a special CPU privilege mode called kernel mode, which is one of the first important things that you actually have to remember for this lecture. And that allows you to actually execute instructions that actually interact directly with the hardware. So different architectures have different name for this mode. It's called S mode on RISC-V or ARM. It's just, they call it supervisor mode instead of kernel mode. means the same thing. And it's kind of a circular or cyclical definition, is the kernel is the part of your operating system that runs in kernel mode. Simple definition. So that's the software that's actually running in a more privileged CPU mode called kernel mode. These instructions only run because that software, that core part of your operating system is trusted. It's written by, if it's a Mac, it's written by Apple. If you're using Windows, it's written by Microsoft. If you're using Linux, it's written by hundreds and thousands of very, very smart people. And those instructions and that software is the only thing that can actually interact directly with the hardware. So only the kernel can manage virtual memory. If your processes could mess with virtual memory, they could read other processes' memory, and then you'd have no security on your system whatsoever, and things could interact badly with each other. So this is a very, very important part of the operating system. Only thing that can interact with hardware, and only thing that actually maintains security. So more privileged CPU modes can access more instructions. So the normal CPU mode is called user mode. That's what you've been using so far. That's where applications and libraries execute in. It's least privileged. It can't actually access hardware. Then there's kernel mode or supervisor mode. That's where the kernel lives, or part of the operating system. That actually interacts directly with hardware. Later in this course, we'll explain hypervisor mode. So that's where virtual machines exist when we finally get into being able to talk about that. And then there's machine mode, which is the most privileged, that can access everything. That's where your bootloader and firmware is. Or when you did a low-level hardware course, you were just writing things essentially in machine mode without any restrictions. So, oh, yeah.
So is that just to, demonstrate the privilege levels, or is there actually overlap between, say, the firmware and the kernel?
So this is just to indicate privilege levels. So each level below can access all the instructions in the level above. So like least privilege would be like an add instruction or something like that, right? So the kernel can actually use an add instructions, but there'd be instructions here to actually access hardware that these couldn't run. So they're supersets of each other as you go down. All right, so system calls. It's the only way to actually transition between user mode and kernel mode. So it's the only way you can actually interact with the operating system to actually interact with hardware on your behalf. So at the time of doing this slide, you can think of them as system calls as just normal functions if you want. The only thing your program can use is these 456 total different functions. Some of them we've already encountered, like read and write, open, close. By the end of this course, we'll understand all of these. Other ones we've hit is exit. And then there's a few other ones. Again, by the end of this course, this is where the course kind of lies. We'll be living in user space, writing programs in user space that use system calls, and then explaining through lectures what actually goes on in kernel space without actually writing any kernel code. So the nice thing about system calls is no matter what language I write a program in, every single program has to go through that system call interface no matter what, because that's the only way to interact with hardware. So on Linux, there is a way to actually see what system calls every single process makes when you run it using this strace command, which is a really fun command because we can strace literally any single program, no matter what language it's written in. So if I want, I can strace my hello world program. I'm going to do one number dev null. Basically, this just says, I don't care what the output of the actual program is, so I don't want to see hello world. I just want to see what system calls it makes. So if I run it, the first system call, so there's one system call per line. It shows you the function and then all the arguments and then equal and then what the return value is. In this case, I didn't make this system call, so we can ignore this first line. This is basically how someone started running this program. We'll get into that in a bit. But this is what my actual program did. It did write to file descriptor 1, hello world 12 bytes, and then write actually returns the number of bytes written, so you can actually check that every byte was written. Spoiler alert, printf also returns the number of bytes written, so you can actually check if there is an error with printf. How many of you have ever checked if there is an error with printf? Yeah, none of you? So errors can happen with printf, but you've just ignored them. And then here we have exit group of 0, and then that is my hello world program, right? This is all it should do. Well, I can use strace, and I can see what the hell C is doing with its many bytes. So, oops, div null. So I can do the same thing. I can strace my hello world program from C. So I can see it ends, because anything that prints hello world has to end with the same thing because it uses a system call, ends with write file descriptor 1, hello world 12 bytes, and then an exit group. But I can also see other things C did. So if I scroll up, these are other system calls C made. So this, it didn't do. This is me running the program, but we can actually kind of take a guess at what some of the other system calls are. So this is BRK, short for break. It's breaking something. Don't know why it's doing that. mmap, don't know what that is. LD preload. Oh, no, it got an error, no such file directory, so that didn't help it there. Oh, it's using a cache. I don't know. Caches are good, right? It got the value there. That's great, I guess. Then, oh, hey, that makes sense. It opened the standard C library. That makes sense. I wrote it in C. Has to load the standard C library. That explains something. And I can see that it read information. So the file descriptor it got back for the standard C library was 3. Here it's reading the standard C library. And by default, the output here, it kind of looks like an ELF file, but not exactly. That's because by default, anything it can't print out in ASCII is in octal for some reason. I don't know why, but 177 is the same is octal for that same 7F in hex. Again, don't tell me why it's an octal, but it is. Basically, it just means that the standard C library is an ELF file, and then it reads some information from it. Cool. Spoiler alert, it's looking for printf. So it's basically looking for printf, does a whole bunch of stuff, does a whole bunch of stuff, does a whole bunch of other stuff we can't explain yet. You know, ooh, it did something inappropriate ioctal. Ooh, that's not good. Random, I don't know, I'm not using any random stuff, but I got random. Then did this BRK thing, and then BRK for an address. What that's doing is that's actually managing the heap. So this is how the standard C library grows the heap. It is a system call. So BRK with null, that returns the address that starts the heap. And this is basically just the standard C library saying, please grow the heap for me because I need some space for memory. So this is the heap. Yeah?
Why does it use SBRK?
So yes, question is why it doesn't use SBRK. That's because he took another course. SBRK is just a nice way to use BRK. But there's only one system call. So with this, we can actually see what different programming languages do, right? There's no reason why I can't write hello world in Python, right? This should do the same thing. Let's see what Python does. So I can strace Python hello world. So we can see what Python does. We can scroll up and see. So at the end, Python did exit group to exit this process. Did some weird memory stuff, but eventually it did the same write to hello world. So no matter what language it's written in, it eventually did that. You can see Python did some other stuff. So here's Python's an interpreted language, so it had to read the Python file. So here's it doing that. It seems to actually read the same file twice. Bit weird. But you can actually discover what Python is actually doing. So you can scroll up. You can see that it does a lot of other things. So it does a lot of other things. So I've previously just seen how many lines they have. If I count the number of lines for C, it does like 38 system calls. If I look at the Python version and see how many system calls it does 472. Well, fun thing I could do is, JavaScript's a language. It's a pretty crappy language, but it's a language. Should do the same thing, right? So let's have some fun. Let's strace hello world written in JavaScript. So let's strace this. This is always fun. Holy crap. So it ended with exit group. Does anyone see a write to hello world anywhere here? No. It's doing some weird things. So I'm going to start scrolling up. Stop me once you see JavaScript printing hello world. So let's go up one screen. Anyone see write in there? Seeing a whole bunch of other crap. Nope, we're all good, no writes. All right, so let's scroll up a bit more. There's a write up here, but it's a write to file descriptor 14 with a bunch of random zeros and ones. Don't know what the hell that is. All right, nope. Scroll up. Definitely not a write there. Keep scrolling up. Wow, JavaScript sucks. All right, scrolling up. All right, bunch of I think JavaScript got worse. Holy crap. All right, there's something with the heap. Reading, no, not quite there. It wrote a star. It read a star. Cool. All right, JavaScript, oh, there it is. So it wrote hello world, and then it started playing with stars for some reason. And then before, it also started playing with stars. This is what JavaScript does. So now you can unravel the mystery of JavaScript. Can't unravel the mystery of why the hell they wrote it like this, but this is what it actually does. And if we look through it, we can see what it did. So how many system calls does JavaScript make? 952. So it's objectively at least 2 times worse than Python. Fun. So you can strace anything you want and see what it actually does. But at the end of the day, if you write hello world, it's going to do the same things. It has to do write to file descriptor 1, 12 bytes, hello world, and then eventually exit. So back to content. You can think of the kernel as like a long-running process. So writing kernel code is more like writing library code. The kernel, we won't be writing kernel code in this course because it's really, really hard to debug and get right. We'll just be explaining what it does and kind of simulating it. But the kernel lets you load code into it while it's running called modules. Then that code executes on demand. So for instance, when new hardware is plugged in, when you plug in a mouse or something like that, or accessing a certain file, it will know to run the function you just loaded. If you write a kernel module, there's some demos for that. You are running in kernel mode. You can actually access all those privileged instructions. Any kernel data, you could do anything, and you can really mess things up. So you can read the memory of any single process. You can kill any process. You can do whatever you want. You are all powerful. So there are different ways to architecture kernel. This is an important thing that might be like a short answer at some point. So there's different ways to architect the kernel. So there's the first one, which is what Linux uses, called a monolithic kernel. And that basically just says anything that's even related to hardware, I'm going to run in kernel mode. So the kernel that's running in that privileged CPU mode will deal with handling virtual memory. We'll deal with scheduling what process to run on a CPU. We'll deal with IPC. We'll deal with how you actually deal with data on your hard drive and any other device drivers like video cards or anything like that. That will all run in kernel space. So that is an absolutely massive amount of code that is in there. And as we all know, the more code you write, the more errors you might have. the more exploits there might be. And if you can exploit the kernel, you run in kernel mode, you now have full control over that machine. So there is another view of thought that is, well, let's move as much as we can out of kernel space and only run the minimum amount of services required for an operating system. So there's less code running in kernel mode. Less code means less vectors for exploits, hopefully, and that means a more secure operating system. So things that have to be in kernel space are dealing with virtual memory because it needs to be more privileged than anything else to control virtual memory for processes. Also, it needs to be the thing controlling which process to actually run, what program to actually run. Otherwise, if programs can schedule themselves and take over a CPU, then, well, you have no control anymore. And to make sure processes are isolated, it has to have at least some basic form of IPC in kernel space. And this architecture of a kernel that only has these three things is called a microkernel. And that idea is minimum amount of stuff in kernel mode. Try and put file systems, device drivers, and more advanced forms of IPC all in user mode. And then I have to do system calls. So there's other types of kernels that there's different trade-offs for why you would put different code in different modes. So hybrid kernels are kind of in between monolithic kernels and microkernels. So for instance, in Windows, emulation services are in user mode. For macOS, device drivers are in user mode because Apple doesn't want you to be able to modify or touch the kernel in any aspect, so they don't allow you to write kernel code. They lock it down. Device drivers only run in user mode. And there's also active fields of research in operating systems to kind of shrink a microkernel down. Just come up with other names called, like, make it even smaller. We'll call it a nanokernel or a picokernel. And that's the idea of just shoving more stuff into user mode than traditional microkernels. But that is a line of active research. There's different architectural lines you can draw with different trade-offs. So in summary, the kernel interfaces that operates between the system, like CPU mode boundaries, user mode, and kernel mode. You do it through something called a system call. The kernel is the part of the OS that interacts directly with the hardware. Again, cyclical definition, it actually runs in kernel mode. System calls are the interface between user mode and kernel mode. Every single program, especially on Linux, must use this interface. So we can use something like strace to actually see what every single process is doing. And then, we could have, oh, yep.
So, sorry, keep going on.
No, go for it.
Just on the last point, so, with a microkernel, there's certain things that are system related that we don't actually have to input kernel mode for?
Yeah, so like for microkernel, I could put file systems and stuff in user mode and just say, hey, kernel, this is how you read, a disk or something like that. You can read it on my behalf, but you deal with the hardware. But I'll tell you what to do, but I don't actually get to run in kernel mode. I just get to kind of tell you how it works. Yeah. And so what you don't need to know is file formats and how to actually define an executable. But I showed you how to do it in 168 bytes. Should kind of know the difference between the API and ABI at a high level, how to explore system calls. So strace is fun, really fun to strace any single program. And then there's different kernel architectures that shift how much code runs in kernel mode versus user mode, and that will make more sense to you as the course goes on. So just to show and probably end the lecture, whoops, that crashed. So I could literally strace everything. So Firefox is running. I can strace Firefox if I want. If I strace Firefox, well, it's going to slow down because Firefox does a lot of system calls, but I can actually see what it's doing. It's running. It's going to be slow because it's tracing stuff, but here it is. It's still loading. It's still doing stuff. Web browsers do a lot of stuff. Sorry, we're having trouble. And it crashed. Cool. So generated way too much input and crashed that, but if I gave it more memory, it could probably survive. But you can literally strace anything you want.